Today we're going to look at applying some momentum to collisions, and today we're just look at one-dimensional collisions, and later we'll look at angles and vectors involved for 2 dimensions. So the idea is we can measure the momentum of objects after they collide, before and after, and figure out missing things like speeds and directions and whatever. So we'll get to a few examples in a minute, but the key idea is when we're talking about collisions, we're talking about 2 or more objects that strike into each other, and we're going to do it in one dimension today, so that means they're going to be like head-on, or one's going to hit the other object from behind, or whatever. Both can be moving, one could be stopped, one could be moving, it just depends on the scenario. But the key idea is when they collide, they're going to exert a large force over a short period of time on one another, which means if we change the force, we're going to change the momentum, so a change of momentum will be impulse. So we're only going to look at linear collisions or one-dimensional collisions for today. So back in Newton's time, they noticed that the total momentum before the collision of all the objects, so if there's 2 objects that are colliding, the momentums of each of them added together before is also equal to the total momentum afterwards. So we end up getting basically the conservation of momentum. We talked about conservation of energy in Physics 20. Now we're going to look at conservation of momentum. So when objects collide, if they're in an isolated system, which means that we have no energy entering or leaving, so it's sort of a system where all the energy stays constant, the total amount, that means that we have no other external forces acting at play. If that's the case, our total momentum before and after is conserved, so the totals before and after are the same. So let's look at how some formulas are going to be used for this. So before the collision, we would have, let's call it object A, so we'd have the momentum of object A, but we're also going to have the momentum of object B. So those 2 momentums, before and after, is going to give us some sort of total. And then we know that those momentums after, they're going to change. We'll use prime. So PA dash or prime, so that's our momentum of object A afterwards. And then we have momentum of object B afterwards. And the formula is that the total before has to equal the total afterwards, so that means those 2 are the same. So the momentum of A and B added together equals the A and B afterwards of the collision, and those are the same totals. So we can even break this down further if the question is dealing with masses and velocities. So we could say the mass and velocity of object A plus the mass times velocity of object B has to equal mass of A and velocity. I guess the mass will stay the same. We're typically not changing the masses, so the mass of A afterwards will be the same, and then we have velocity of A afterwards will be different, and then we have mass of B and velocity of B. Okay, so that's basically how we're going to deal with these kind of questions. So you're going to use either one or both of the formulas. Usually we use the mass and velocity one, that's the most common, because typically the questions are going to be saying things like, what is the final velocity of object A, or something along those lines. So let's do a couple examples. The first example is where we're going to get 2 objects that are going to strike and bounce apart. And then the second example is we're going to look when 2 objects strike but stick together. So both of them are similar, but you have to be a little bit careful when you're solving them. So this first one is we got 2 pool balls. We got a billiard ball moving to the right. It hits another one that's stopped, and the question is, what's the velocity of the red ball afterwards? So if we set this up, I'll even do it in color so we can keep track of this a little bit better. So we're going to have mass of A times velocity of A plus the mass of B and velocity of B before, and that'll equal our mass and velocity after. So let's write those in like that. So now let's substitute it in. So our mass of the first one was 0.15, and its velocity was 8, and our mass of the red one, it says is similar, so that'll be the same size. So right, pool balls are the same size, so it'll be 0.15, but it's at rest, which will be 0. So that means that whole thing will be 0. So then on our right hand side we've got the same mass, and this time it says it's moving to the right. We've got to be careful. So moving to the right, we consider that positive. So our velocity originally was positive 8. It's still moving to the right, so that'll be positive 2.5. And then our red ball has the same mass, 0.15. And the question is, what's its velocity? So you can see we plug everything in the formula. We have everything except for the final velocity of ball B. So now all we have to do is do the math, solve all this. So if we go 0.15 times 8, gives us 1.2, and that's our momentum, so we don't have to worry about units. This one is 0, so we can ignore that. And now we go 0.15 times 2.5. That gives us 0.375 plus 0.15 VB prime. So if we do the math, let's subtract the 0.375. So 1.2 minus 0.375 gives us 0.825. And we're going to divide by 0.15. And that gives us a final answer of 5.5. And since we're looking for velocity, that is meters per second. And if we can't be careful with the symbols, or the directions, the positive and negatives, so this works out, we got a positive 5.5, so that means it's going 5.5 to the right, right? Because we called right our positive direction, so it's also going to be going right as well. Let's do another example now where the objects stick together. So in this case we got two different masses and they're going to collide and stick together. So let's go through the same formula again. So let's go A plus B equals A afterwards plus B afterwards. Okay. So the only thing that's a little bit different in this case is when we're solving this, the two masses were separate to the start, but then they combine afterwards. So they're going to combine together, and they'll just be one. We're just going to have one big mass. Let's call it mass of A and B together, and it's just going to be moving together as one speed. So that's the only thing that changes with these when they stick together. We're just going to combine the two A and B's into one. And you can write it as AB or just MV, it doesn't really matter. You don't need to worry too much about the symbols. So in this case, let's be careful. So we've got a blue one that's 2.3. And it says it was moving to the right at 12. So 2.3 times 12. Then it says we got a red one that is 5.6. And it was moving to the left at 8.1. So we're going to put that in as negative. So be really careful with the positive and negatives. So now afterwards, the masses are going to stick together. So our total mass will still be the same, but it'll be 5.6 plus 2.3. So that'll give us 7.9 for our total mass. And the question is, what's its total velocity afterwards? So pretty basic question. All we have to do is figure out the left-hand side and divide by 7.9. And I won't bother doing the work on this one. When we plug all that in on our calculator, we should get an answer of negative 2.2. Okay, so we got to be careful with this. Let's think about the logic a little bit with this one. So we had a smaller mass going to the right at 12. and we had a larger mass going to the left at 8.1. Okay, so this one's quite a bit bigger, but it's going a little bit slower. But in essence, though, the total momentum is still bigger. So B had a bigger momentum going in. So when they collide and stick together, because it's got larger momentum, it's going to carry the mass to the left slower. So that's what the negative is telling us, that after they collide, the total mass is going to go to the left. So when objects stick together, you can see just a slight modification of the formula. Add the masses together, and then you just have one mass and one velocity. And it's a common question because quite often we'll have cars or trains or something colliding and they get locked together, so they'll move together as one object. And it's also possible that the objects could be stuck together at the start and then they separate and go into different pieces afterwards. So typically a question like that would be some object that explodes. So let's suppose we have a box that has a certain mass and it's at rest, and it blows up into 3 different pieces that go in different directions, and we'd still do the same type of calculation. But typically we get into different directions and vectors and 2 dimensions in that case. So we'll save those kind of questions for the next lesson. So that's all for today.